IntroAlgebra lesson 1-7B. Last time we were talking about a function and some of the different ways that you could actually describe a function. If you recall, we said that you could have an input-output table, which we discussed. Values go into the function, it's computed, and out comes an answer. You could have a description in words, so we specify in words what's happening with the function. We could have an equation that represents the function, and we can make a graph of the function. So I have here an example of each one of those. Here's an example of it in words. Take any number and add 2. So in words, a description in words, doesn't matter what the value is. If somebody says, all right, apply this function, apply this rule to 100, you would go, well, 100 plus 2, 102. If it said to put it in for negative numbers, wouldn't matter, decimals, fractions, no matter what, take the number and add 2. As an input-output table, it could look like this. So if I put a number in like 1 and I add 2, I'll get 3 output. If I plug a number 2 in, add 2, I get 4 out. 3 in, add 2, 5 out. 4 in, add 2, I get 6 out. Where did these numbers come from? I just made them up. Any number you plug in and use this function, you're going to get outputs. You just add 2 to whatever the input is, no matter what. Alright, so that's an input-output table. We have a description in words. As an equation, it could look like this. So we would put a number in for x, add 2, and we'd get number out. It doesn't matter which side the y is on. If you wrote down x plus 2 equals y, that's the exact same thing. But this is our output. This is the number we plug in so that we can add 2 to it, just like the word said. And lastly, we have a graph. It says up here, we can have a graph to describe a function. So here's a graph of this exact same information. So here, when we had an input of 1, we had an output of 3. When we had an input of 2, output of 4. Input of 3, output of 5. Input of 4, output of 6. And how long would that continue for? It would continue forever going in this direction and forever going in this direction. So these were our in values. These were our out values. All right? So let's look at a specific couple problems here. Now this is going to seem complex, and we get a little bit overwhelmed at sometimes when we have a lot of words. Just don't stress about it, okay? Try to look at for some key information. Always read a story problem more than one time so you know what the question is, then you rewrite it again, and you can reread it again, and you can find out what you're looking for. All right, the temperature at 6 a.m., so in the morning, was 62 degrees Fahrenheit, and it rose 3 degrees Fahrenheit every hour until 9 a.m. Represent the temperature T as a function or a rule of the number of hours. In other words, is there some way of figuring out what the temperature is at each of the hours? All right? So we're going to go through a couple different things. First of all, we'll write an equation for this. Now this doesn't go on forever. It's not like it starts at a certain temperature and then every hour it goes up by 3 forever, because if it went on for like a month, we'd have, insane temperatures. It only goes until 9 a.m. All right? So, we don't want to put in the time like 6 a.m. or 7 a.m. We need to think about this in terms of when we start. So what we want to do is we want to say, okay, this starts at 6 a.m. This isn't the equation, but this is how I'm going to figure out what the equation is. So what you need to think about is if it starts at 6 a.m., how many hours after 6 a.m. is 6 a.m.? The correct answer? 0 hours. No hours have taken place. It's the beginning. So we will call this our 0 hour. Because no time has elapsed. It's still at 6 a.m. All right, if that's 0 hours, then what time is 7 a.m.? 7 a.m. is how many hours later? It would just be 1 hour later. If we keep this logic up, 8 a.m. is 2 hours later. You may be thinking, I don't understand, why are we doing this? Because we can't use these time values when we substitute them into an equation. We have to think about a starting amount, which is always your 0, and how much you're increasing from that in relationship. So 9 a.m., which is our final hour, that's going to be 3 hours. Okay, now let's think about this. How much does it go up every hour? 3 degrees every hour? That kind of makes us think that there's probably some multiplication in here. 3 every hour. If there was 1 hour, it'd be times 3. If there was 2 hours, that times 3. So 3 is multiplied by the hours. And where did it start? It started at 62. So we add on how much it changes to the original 62, and that will equal our temperature. Now let's try it out. We don't want to pay attention to the equation for a second. Let's just look at the times. Right now it's 62 degrees. If it goes up 3 degrees in an hour, what will it be at 7? It will be 65 degrees. Then what will it be at 8 a.m. it'll be 68 degrees, and at 9 a.m. it'll finish off at 71 degrees. So we know that we should be getting values of 62 for the start, 65, 68, 71. If this equation is correct, then when we plug those values in for h, for our time, we should get those values. So let's plug 0 in. If you plug 0 in here, what's 3 times 0? 0. And 0 plus 62 is 62, which is good, because that's what our starting temperature was. We said it should start at 62. If we plug in a 1, 3 times 1 is only 3, because that's only 1 hour later, 3 degrees. 3 degrees plus 62 makes 65. At 7 a.m., it should be 65. Plug in 8 for this h? No. Plug in the 2, because that's 2 hours later. 3 times 2 is 6. 6 plus 62 is 68. Again, that's the value we thought we would have at 8 a.m. At 9 a.m., we thought this should be 71. So let's plug a 3 in. 3 times 3 is 9. 9 plus 62, good enough, 71. So we think this equation is pretty solid. All right, next, we make an input-output table. Now we've already kind of done this, so it should be easy. Again, we plug 0 in, 0 plus 62, 62 degrees. We plug a 1 in, 3 times 1 is 3, plus 62 is 65. We plug a 2 in, 3 times 2 is 6, 6 plus 62 is 68. Now someone might say, hey, I see a pattern. It's going up by 3 every time. That's good. It should be going up by 3 every hour. If it's not, we've probably done something wrong. So in the final hour, right here, it's going to be 71. Remember, this is representing 6 a.m. This is representing 7 a.m., 8 a.m., and 9 a.m. Again, some people want to know, why don't we just stick 9 in for time? If you stick 9 in for time, you're saying it's 9 hours later. And that's not what we want. We really only want 3 hours later. 3 times 9 would be 27. 27 plus 62, that's 89 degrees. Do we think if it's only going up 3 degrees each time, that would be correct? That's way too much. So these are hours since the start. 0 hours since the start. 1 hour since the start. 2 hours since the start. 3 hours since the start. That's where those values are coming from. All right, and lastly, make a line graph. Well, the hours across the bottom. At 0 hours, we are at 62 degrees. That's where this started. Then at 1, it's at 65. At 2, it's at 68. And at 3 hours, which again is 9 o'clock, it's 71. Right there. All you need to do then, if you want, is you can connect them with the line graph. And there we have it. So we have the whole function described as an equation, an input-output table, and as a line graph. 3 different ways. The only thing that's missing is in words, but in a way, the words are up here in the story problem. Now let's try one more. Now, it's key that you understand that starting point is 0, and then we increase from there. So, a plane is at 2,000 feet. So an airplane's flying at 2,000 feet. It climbs, which means it's going up, at a rate of 1,000 feet every minute. So here's the plane flying at 2,000. 1 minute later, it's at 3,000. 1 minute later, it's at 4,000. 1 minute later, it's at 5,000. And it's going to do this for a total of 4 minutes. That's it. It's not going to go forever, just for 4 minutes. The altitude, h stands for height, altitude, for t, time, minutes, is given by this equation. H, the height, is 2,000 plus 1,000 t. Now, I've already given you the equation. The last time we had to make an equation. Now it's given to us. what this is saying is this is where you started. This was our starting point. So this was the start. The 1,000 is how much it's changing every minute. So this is the change per minute, which is right here. Remember, T stands for time, and it's in minutes. It says right here, T minutes. And H is the altitude, which we're going to say is in feet. So that's the altitude in feet. Why does it start at 2,000? Why does it have 2,000 being added on? Because the plane's already at 2,000. 1,000 is being multiplied by the time. Now here's the tricky part. People look at this right here and they're going, I don't have any idea what that means. It says T, remember T stands for minutes, is greater than or equal to 0, which means it could be 0. Greater than or equal to 0 means it could be that value. And if we were talking about 0 time, we'd be talking about the start, because no time has taken place. But it can also be 4 minutes, because it says T is less than or equal to 4, because this is taking place for up to 4 minutes. So time is somewhere between 0 and 4. 0, 1, 2, 3, or 4. It can be any of those values for time. All right? So first of all, we'll make a table. So our time can be 0 minutes. That's the start. If you recall, we would start here. Because nothing's happened if it's 0 time. It hasn't changed. 1 minute later, 2 minutes later, 3 minutes later, 4 minutes later. And why doesn't it go past 4? Because this only happens for 4 minutes. So let's try it out. Plug the 0 in. If you plug a 0 in, what is 1,000 times 0? Hopefully you get 0. And if you add that 0 plus 2,000, you'll get 2,000. Which would make sense, because if we haven't done anything as far as time, we're still at the cruising altitude of 2,000 feet. Now 1 minute later, what should the altitude be? It should be 1,000 feet more at 3,000 feet. But if we try it, plug the 1 in. 1,000 times 1 is 1,000, and that 1,000 plus 2,000 makes 3,000. So it seems logical. Another minute later, it'll be at 4,000 feet. Try it out. 2 times 1,000 is 2,000, plus 2,000 is 4,000. We're good so far. 3 times 1,000, 3,000, plus 2,000 makes 5,000. Again, somebody might say at this point, or maybe earlier, I recognize a pattern. It's going up by 1,000 every minute. Remember, these are minutes. This is altitude. 1,000 every one of these minutes. That's good. It says right here that it goes and it climbs at a rate of 1,000 feet for every 4 minutes. So 6,000 feet would have to be here. Which fits the logic. And lastly, we'll make a graph of this information, because that's another way we can represent a function. At 0 time, we're at 2,000 feet. Because that's what it began at. At 0 time, we're at 2,000 feet. 1 minute later, we're at 3,000. At 2 minutes, we're up to 4,000 feet. I don't have that one at 3,000. 3,000 is halfway between. Okay, so at 1 minute it's here. At 2 minutes it's at 4,000. And at 3 minutes it'll be at 5,000. And at 4 minutes it will be at 6,000. And if we connect it, that would represent the function. So for any one of these moments, of 1 minute later, 3,000, 2 minutes, 4,000, 3 minutes, 5,000, 4 minutes later, the plane is now cruising at 6,000 feet. Again, story problems are tough, but if you break them down into the simple pieces and the most important parts and get rid of all the noise, and you concentrate on what you know, they get easier with practice. They aren't going to be perfect the first time through. You've got to work at them, work at them, work at them.